All right, so we're starting into another chapter today. So chapter 19. So we've got a new Learn Smart going. We've got homework this week. And our big thing to look forward to is that we have, let's quiet down please, is that we have an exam starting next Monday. Okay, so that's all set up at the testing center. Schedule is just like it was last time. We've got the written test on Monday in class. I already sent out room assignments. I'm really on top of it this time. I made a change on how we're going to, how you're going to write your information on the exam, so how I'm going to pass it back as well. Okay, let's quiet down, please. I think the way I'd always done it for years, just passing it out here, even though the names are on the back or buried inside and the scores is not really up to snuff these days with the FERPA, trying to maintain everybody's privacy. So what I've done is I sent out an announcement yesterday assigning each of you what I call an exam number. Okay, so look at that announcement. You need to know what your exam number is when you come to take the exam. So instead of writing your name on the exam, you'll write your exam number. All right, you'll do that on the front page, and then on the score page, so it's inside the last page where the scores are written, you're going to write your exam number and your A number. Okay? And then when I pass them back, I'll just order them in order of this exam number, right? So your name won't be anywhere, and so if somebody stumbles upon your exam, they don't know who got what score or anything like that, right? So we'll maintain everybody's privacy. All right, any questions on that? Okay, so we're going to have 2 review sessions this week. We're still working on scheduling. The first review session should be tomorrow night. We still are trying to reserve a room. So from 7 to 9, Friday will be the super session. And I need to talk to Jake. Is he here? Do we know what time that's going to be? 4:30 to 6:30. 4:30? We're working on a room. Okay. So 4:30, oops, dang, right, 4:30 to 6:30, oops. Okay, and we'll send out an announcement on the room or announce it tomorrow or whatever. All right, so back to the schedule, just like last time, starting Monday after our written exam is done until Wednesday night. You'll have an opportunity to go to the testing center to take the computer portion of the exam, right? And then from Wednesday night until Friday night, if you so choose, you can repeat or revise the computer portion of the exam, okay? All right. So we just finished off talking about aromatic chemistry. So we did quite a bit of new chemistry there. We looked at electrophilic substitution reactions. We looked at the activating, deactivating, and directing characteristics of different substituents on the ring. So if we add a second or a third substituent onto that ring, we know where it's going to go. So that allows us to do more synthesis. All right, so there will be a synthesis type of problem on this exam, and so it will start with benzene and it will build things up, though it may require some modification of a side group like we've talked about. All right. So what we're going to talk about now, and so this is going to be a little bit of a change of pace, and this is kind of a entry into a whole bunch of chapters that are all on carbonyl groups. So a carbon-oxygen double bond, this is called a carbonyl. All right, and there's a whole bunch of functional groups that have this as part of their structure. Okay, so we're going to start out with the first group of those, and those are the carboxylic acids. And we've seen those before. You saw them all the way back in chapter 2 or something like that, where we talked about acid-base chemistry. Okay, so we're going to review a little bit more of that. We're going to talk about today some naming of those carboxylic acids, and then we're going to talk about reactivity leading up to the acid-base chemistry of not only carboxylic acids, but the name of the chapter is and the acidity of the OH group. So that we're going to also include phenols in that, which is a benzene ring, like we know, with an OH on it. Okay, so these are systems where conjugate bases are stabilized by resonance. All right? Okay, so before we do that, let's do our clicker for today. All right, so learning objectives here. First, so the first thing we do, even before naming, we're just going to review what the functional group is, right? And what its structure looks like. Then we're going to do a little bit of naming, and then we are going to talk about methods to actually synthesize carboxylic acids, right? And this is just a review of reactions we've learned before. All right, so carboxylic acids are really the most common organic acids. All right. In general, we think of them as reasonably strong organic acids, but as far as the bigger picture of acids go, they're not that strong. Okay. They are very well represented in nature. You know, they're very common functional groups. So here's the basic functional group right here. Right here. All right, and we know that when the carboxylic acid donates its proton, it gets a conjugate base that looks like this. And we'll talk about what it can do a little bit in a minute. All right, so another common acid is acetic acid. So where's acetic acid commonly found? It's in vinegar, right? Here's something about its structure. The carbonyl carbon is sp2 hybridized, and so the bond angles are roughly 120 degrees. All right, notice that for the carboxylic acid itself, that the carbon-oxygen double bond length is shorter than the carbon-oxygen single bond length, right? But what do you think happens once we form this conjugate base? This is called the carboxylate. Are the bond lengths still different when we get down to this conjugate base? No, because we have resonance. Let's just go ahead and write that out. We have resonance. So these electrons can be delocalized between the two oxygens. Like this. And so the hybrid structure has essentially 1.5 bonds going to each oxygen and 1/2 of a charge. Okay, so once we make this carboxylate anion, the two carbon-oxygen bonds would be equivalent to one another, the same length, the same strength. All right, another common acid is this one. This is like the smallest of the carboxylic acids. So anybody know the common name for this structure? All right, this is formic acid. And do you know what kind of organisms produce formic acid? Huh? Ants do. So ants, the red ants and these biting ants, they produce formic acid, so then they bite and then they essentially bend their abdomen around and spray formic acid in the wound. All right? And so I have a little story about ants and formic acid. So when I was a grad student, we were studying insects. Maybe I told you about that before. But several times I had the chance to go to Florida to collect insects. And this one time I went it was actually with a class. It was over spring break, and it was like a 1-credit class. And not really my advisor, but his collaborator, who was a biologist, was leading the class. And it was really amazing. We went to Lake Placid, Florida, right? Lake Placid, you've heard of that before? That's where they had the Winter Olympics. In Florida, right? But we'd walk around, there's just these sandy kind of fire roads and stuff. He'd walk around, lead us around, and he'd come to a plant, he'd turn over a leaf, and every time he turned over a leaf, there would be an insect stuck to the bottom of it. And then he would tell us the whole story about their life and everything like that. And they had a lot of interesting things. Like, for example, there was this one little insect. You couldn't really see it. He had all this curly brown stuff stuck on its back. And in fact, that insect would just stick all of its feces onto its back. So it wasn't very tasty, like you might imagine. But one time, we came to this big anthill, and he was telling us the story about formic acid and all this stuff. And to demonstrate how, they bite and spray, he didn't just pick up one ant and put it on his arm. He stuck his whole arm all the way down into this anthill and pulled it out, and there must have been 500 ants biting and spraying on his arm. But I think he really it was a little more than he expected, and he turned all pale and had to sit down and rub all those things off. It was the high point of the whole week, really. So formic acid. All right, so when we name carboxylic acids, many of the carboxylic acids have common names. They give them all the way up to 8 or 10 carbons in the book. I think if we can just remember these two small ones, this is formic, the one we just talked about. And this is acetic. And I'm not going to actually test you on these common names, but these are common names. So they're, just being a basic citizen of the world, you should know what acetic acid is. All right? But those are not their only names, right? We have IUPAC naming as well. And the way that the IUPAC naming goes is we essentially take the parent structure, the alkane name, we drop the E off the end, and we add oic acid. So we've added this part as the suffix. All right? So if we looked at formic acid, what would its IUPAC name be? We take a 1-carbon alkane, which is methane. We drop the E. We had oic acid. Right? Methanoic. Noic acid. Right? Nobody calls it that because everybody knows it's formic acid, but that's what its IUPAC name would be. What about acetic acid? Ethanoic. All right, so what if we do a longer acid like this, right? So we're going to find the longest chain that includes the carboxylic acid. And the carboxylic acid is always going to get the number 1 position. Okay, so we're just going to do this longer chain. We're going to number this 1, 2, 3, 4, 5, 6. So what would be the parent acid for this? Hexanoic acid, right? So this would be, I'm not going to have enough room in here though, all right. I'll start out with and then we have one substituent on here, right? So this would be 3-methyl hexanoic acid. All right? Yeah.
Question, don't they have like Greek letter abbreviations?
Oh, I think what they did, okay, so the question was, in the book they use some Greek letters. I don't think we necessarily want to use those for naming. I wouldn't say. We'd use numbers. But sometimes we refer to different positions along the chain by, alpha, beta, gamma, delta. So usually what we would do is the position adjacent to the carbonyl group would be called the alpha position. Okay? And we'll find later that the alpha position has special properties. Okay? Its own reactivities. And then we just go beta, alpha, beta, gamma, delta. So it's a term that we can talk about different positions relative to where the carbonyl is. All right? So this last acid on the right, upper right, we know that one already, right? What's that one called? Benzoic acid. Okay, when we have carboxylic acids that are just attached to other rings, not a benzene ring, what we do is we name the ring and then we just add carboxylic acid. Okay, so this would be a cyclohexane carboxylic acid. Okay, cyclohexane, and then you just add it on. Carboxylic acid. Okay, so that would be the base structure right here. Okay, if there's substituents on the ring, then we number the ring starting at the position where the carboxylic acid is attached. Okay, and then we'll just number around the ring to give the substituent the lowest number. So we just number this 1, 2, 3 over here. Okay, so we'd have a methyl group at position 3. 3-methyl cyclohexane carboxylic acid. All right, so this structure shows some stereochemistry though. So if we weren't worried about what we'd call the absolute stereochemistry, whether it's R or S, but we just wanted to describe that these two groups are on opposite sides, how would we do that? Trans, right? So we just put trans out in front. So trans 3-methyl cyclohexane carboxylic acid. Okay? All right, so carboxylic acid salts are really just the conjugate bases of carboxylic acids. And they're usually salts because the conjugate base has a minus charge and you need some type of counter ion, a cation to go with it. So we name those like we would name salts, and so we list first the cation, then the anion. Okay, so for example, if we had something like, I guess I could look at what example I have in here. If we just had something like this, O minus, and let's say we have a sodium here. So for example, we took this carboxylic acid, treated it with sodium hydroxide. Right? Hydroxide pulls off the proton to form water, and the sodium goes from being associated with the hydroxide to be associated with the carboxylate. Right? Just follows the minus charge around. So we're going to name this with sodium. This is the cation first. And then what we do is I'm going to do it like I did before. The alkane. We're going to drop the E here. And we're going to add, I don't know if I can fit it though, alkane O-weight. Okay, we don't need an acid on the end or anything. So if we were doing this one down here, this would be 1, 2, 3, be the 4-carbon acid, right? The 4-carbon alkane is butane. So this would be butanoate. Okay? That tells us here, if this O8 is here, that tells us we have to come back and look at what's in front. Okay? In fact, when we learn how to name esters, we're going to do it in the same way. Okay, and then if we had something like this one, right, if it's from acetic acid, let's put a lithium for this one. We could call this just lithium acetate. So acetate is the common name for the conjugate base of acetic acid. All right? Questions? Yeah.
So could we call this lithium ethanoate as well, or would that?
Yeah, you could. So the question was, could you, so to really follow the IUPAC, then this would be an ethane. We drop the E, ethanoate. Right, lithium ethanoate. That would be fine. All right, so the first type of reactions we're going to look at here is we're going to just review how we can make carboxylic acids. Okay, we'll be learning more of these, but this is our starting point. Okay, so the first way we learned how to make a carboxylic acid was by the oxidation of a primary alcohol with a strong oxidizing reagent. All right, so one example of this strong oxidizing agent was potassium dichromate. We could also use chromium trioxide and sulfuric acid. Those basically form the same oxidizing agent. Remember, when we oxidize a primary alcohol, it goes through an intermediate as well. What's the intermediate functional group? So if we oxidize an alcohol, primary alcohol once, what do we get? Okay, so the first oxidation, remember during oxidation, we're going to either remove hydrogens or we're going to add oxygen. Okay, so if we remove 2 hydrogens, we're going to remove 1 hydrogen from here and this hydrogen here. So we're going to remove these 2. We're going to form a double bond. Right, and we still have 1 H there. Okay, so what functional group is this? An aldehyde. Okay, but if we're using a strong oxidizing reagent like this, it never stops at the aldehyde. Okay, the aldehyde gets oxidized again. Right, and in the second step, it essentially ends up adding another oxygen. And we get our carboxylic acid. Okay? Another way to form carboxylic acids was what we learned in this last chapter. And this was the benzylic oxidation. Right? We used potassium permanganate. And remember, what it did was it oxidizes at the benzylic position all the way to the benzoic acid. Okay, so we're just really looking at or paying attention to this piece here, and essentially we end up losing this ethyl group as something, probably an acid or something. Okay, so remember as well, we could start with even something like this, right? And if we use the same conditions, that will oxidize to a carboxylic acid, right? But what happens if we have a tertiary? Let's put a different one there. If we try to do this same thing, no reaction. Okay, this does not go because it needs a proton at the benzylic position in order to be oxidized. Okay? On one of the old exams, and I just also this morning sent out an announcement for what problems from the old exams are relevant for our exam, is that you can also use these chromic acid or chromium trioxide reagents for this. And so let's say, use something like this. Okay, or it might be listed as HCrO4. Okay, so these are just to make the problems relevant, right? You could use these if you want, but when you see these on the old exam, you can think about potassium permanganate, just as the same thing. Okay? All right, so this is another way to make a carbon. You learned last semester, I believe. And this was this tricky ozonolysis reaction, right? And so if we do an ozonolysis, on an alkyne, remember this is an oxidative cleavage, so it's going to cleave this bond right here, and it's going to give us two different pieces. The piece that's has the alkyl group attached is going to go to a carboxylic acid. All right? And the other piece would go to formic acid, but it gets oxidized again. Okay? And what does that give us? Carbon dioxide. All right? If we did the same reaction with something like this, where we had another group on the end, right? We wouldn't get carbon dioxide, but we would split this bond right down the middle, and we would get two different carboxylic acids. Right? So we would get this carboxylic acid and this carboxylic acid. Okay? So, if we can make it to any of these functional groups, right? If we have some other functional group and we want to convert it to a carboxylic acid. So, for example, let's just cross this out. What if we wanted to convert this alkene to to this carboxylic acid? How might we be able to do that? Yeah.
We could brominate it with elemental bromine.
Okay. So if we did that, I'm going to draw it down like this. So Br2 puts two bromines on.
And then we'd eliminate both of those.
We eliminate both of them. Minus, and we do this 2 times. Okay, this would form this alkyne. Can we do that? Does that give that?
Oh, wait.
That doesn't give that, does it? It would give a carboxylic acid, but what's wrong? It's missing a carbon, right? So that doesn't actually get us to that. So how could we get to there?
Sodium hydride.
With sodium. Treat what with sodium hydride?
You could treat the alkyne sodium hydride so that it has a negative charge, and then treat that with bromine iodide.
Yeah, no, I think we're wandering off base. Yeah.
We could use hydrogen in the palladium catalyst to convert it to an alkane.
Yeah.
Then we could we could treat that with a carbon triple bond to add another carbon on there, and then we could do the ozonolysis.
Well, we can't go from an alkane. Alkanes are essentially unreactive, right? The only reaction of an alkane that we have, we could either burn it, and we could get the CO2 up here if we wanted, or we could do a radical halogenation. Those are the only things we can do for an alkane. Yeah.
I think if we are able to turn it into a primary alcohol, then we'll be able to just oxidize that. So all we need to do is do BH3 with H2O2.
Right.
And then that will get us a primary alcohol, and then we can oxidize that like we learned in class.
Right. So what's this reaction called? This is a hydroboration oxidation. Remember, it does a hydration reaction, but it's in an anti-Markovnikov fashion. Puts the OH on the less substituted position. So it would go to here, and then we could do the oxidation. So potassium dichromate. And that would oxidize the alcohol up to the carboxylic acid. Good one. All right. So these other ones are fine, but we just have to make sure how many carbons we need. Right? All right. Well, yeah. I don't think I would be so worried about that part. But yeah, it would be with sulfuric acid.
Sulfuric acid.
All right, so we've learned or reminded ourselves on how we can make carboxylic acid. So let's look at some general reactivities of carboxylic acids. All right, so the obvious thing for a carboxylic acid is to be an acid, right? A proton donor. And so that's what we know them most for. So here's an example. Here's this acid, kind of like benzoic acid. And we're going to treat it with hydroxide. And so the hydroxide is going to react with the acid. And we just get a acid-base reaction here. We get our conjugate base plus our conjugate acid. All right? So that's what we already know. Okay? Carboxylic acids can also be proton acceptors. All right? If it's a proton acceptor, what is it behaving as? As a base, right? So that's weird again. The acid acting as a base, right? So we have two choices here, right? We have two different oxygens. And so either of those, because they both have non-bonding pairs of electrons, either of those oxygens could act as a base, right? But one of them is better at doing this than the other. All right, you guys know which one it is? Somebody says a carbonyl. Everybody agree with that? Do you think the carbonyl oxygen, the oxygen with the double bond, is the more basic position? No, it doesn't seem, nobody's raising their hand.
I said it.
I know, but this is, we talked about this before, this is all democratic here. How many people think it's this oxygen down here that's more basic? Okay, some of you think that, well, we're not going to be democratic. All right, so let's just draw out the conjugate acids and see if we can decide which one would be better, right? Because in this case, we're starting with one base. We're going to go to two different conjugate acids. So whichever conjugate acid is more stable is the one that would be formed preferentially. And that means that the oxygen that picked up the proton would be the more basic position. Okay, so let's draw out the two possibilities. So we'll draw out the possibility for protonating there. Okay, and if we do that, we would get this conjugate acid. I'll draw the non-bonding electrons in here. Alternatively, we could use one of these electrons to protonate, right? And I'll draw this down here. And have a non-bonding pair there, the plus here. Non-bonding like that. Okay, so the question then is, which of these two conjugate acids is more stable?
The bottom one.
The bottom one? So why do you think the bottom one is more stable?
I figure, I'm not sure if this is right, but couldn't the H2O leave as a leaving group and then you'd have an acylium ion?
Right, but so the question was, if we form this, essentially we form this water molecule, we know water molecules can be good leaving groups, so that could come off to form an acylium ion, but isn't an acylium ion very stable relative to these things? Not really, it's not that stable, right? What else could play a role in stability here? Yeah. Yeah, exactly. The top one, look at this. We have, essentially in this top one, let me go to my little pointer here. We have non-bonding electrons on an atom next to a pi bond, right? This is a classic resonance situation. So we can draw these electrons to go down like this to form a pi bond there. And these electrons can go up on the other oxygen. And if we do that, we form another resonance structure that has the double bond down to the other oxygen. Like this. Okay? So, for this top one, we can spread the electrons and the charge between both oxygens. Whereas, can we do that on the bottom one? Well, you know, we could take this pair of electrons and bump it up here, but then we have a 2+ charge on this oxygen and a minus on this oxygen, and that's not going to be very good, right? That's a lot of charge. All right, so the top one has better resonance, okay? And this pair down here is more localized. Okay, so this one is more stable here. Okay, so when we protonate a carboxylic acid, we're always going to protonate it up on the carbonyl oxygen. Okay, that's the more basic position. All right, everybody follow that?
Quick question.
Yeah.
Why can't the electrons in the double bond on the bottom one move down and have resonance with the positive almost like a lily.
Okay, so you mean to push these electrons down here?
The electrons that are in the double bond already.
Oh, just to push them this way?
Yeah.
Well, the problem with pushing electrons towards this oxygen over here is that this oxygen already has a complete octet of electrons. So if we try to move this double bond down and draw it in here, we've added 10 electrons to that oxygen. So that's like a no-go. All right? What do we have? Oh, so this is another thing that we'll find out that we can do later, is that carboxylic acids can also act as electrophiles. Okay? And so in that case, we're going to have some nucleophile, has a pair of electrons, could be neutral, it could have a minus charge or something like that. And if this acts as a nucleophile and not just a base, where do you think it's going to react in this carboxylic acid? Right, the sp2 hybridized carbon, because we know that this carbon-oxygen double bond is polar, right? So that puts a delta minus up on the oxygen and a delta plus on the carbon. So a nucleophile is going to be drawn toward the carbon that has more plus. Okay? So we will see this type of reaction a lot coming up. The challenge with a carboxylic acid is if that nucleophile is very basic, then what's it going to do? Is it going to act as a nucleophile? It's going to act as a, well, yeah, the carboxylic acid would act as an acid. So if the nucleophile is very basic, it's just going to do an acid-base reaction. Okay? And so just in this last minute, just as a little view forward, usually if we want the carboxylic acid to act as an electrophile, we have to make it even more electrophilic. So we catalyze this reaction, and the way we do that is we add acid to it. And if we add acid, where did we say that the carboxylic acid gets protonated? On the carbonyl oxygen. Right? So we get to here, and we showed one resonance sharing the plus between the two oxygens, but there's another resonance structure we can draw as well. Okay? And that has to do with just doing this part of the resonance. We already talked about how that is a polar double bond. Oops, I shouldn't have put that there. And this resonance shows that even more, and it puts the plus on the carbon. All right? So essentially what happens is by protonating the oxygen, we increase the amount of plus held by the carbonyl carbon. And that makes it more electrophilic, and it can then react with a weaker nucleophile. Yeah?
Would the carbon not have a 2+ there because 2 electrons are being moved, or would it just still be a single bond?
No, it would still be, because remember when we calculate formal charge, any bonding pairs, and we only count one of those for that carbon. So, yeah, this would just have a plus here, neutral on top. All right, and so this increases the delta plus there. So more electrophilic. Okay, so I will see you guys tomorrow.